So today we're going to be dwelling on duality and then a few of its applications, and of course at some point we're going to solve the previous exam questions. Not worry about it, but I have to, I want to get rid of this part first. So we will be solving the exam questions later on. Now, when we talk about duality, we're actually talking about the same model, but a bit of a different interpretation of it. So we still have a primal model, the model that we have, constructed with the decision variables and the, constraints and the objective function. The dual of it is actually the same thing with a different economic interpretation. Now, when we're talking about the dual model, we are talking about, instead of a maximization, for example, a minimization problem. So what we are talking about, you will see soon enough, but still, the decision variables in the primal model, in the first model, let's say, is a primal model, which is a maximization, and there is we can write it like this. For example, it's a simple maximization model with everything less than or equal to, with every constraint being less than or equal to, which are normal constraints for a maximization. The dual model actually be something like this. It's of course right subject to, so we know what we're talking about. So this is like EI, let's call it, and something like this. So the primal and the dual are related. They are related like this. Every variable, every decision variable in a primal model is linked to a constraint in the dual model. You will understand what the link is all about when we're talking about examples, and you will see what I'm talking about, but still, every decision variable is linked to a constraint, and every constraint is linked to a decision variable, okay? Vice versa situation. So, when we're talking about the dual model, we are actually switching everything. We are going to take the, you will see transpose of everything, or the matrix in here at least, and then you will see what we're talking about. But still, there are some rules that we need to, consider before we can find the dual. For example, the constraint signs and the decision variable signs over here in the primal model affect signs for constraints and decision variables. Again, we know that the constraints are linked to the decision variables in the dual model, so they affect the sign of the decision variables. And then we know the decision variables are linked to the constraints, so the decision variable signs are affecting the constraint signs. How does that happen? Now, we call this, let's call this at least, normal and abnormal constraints, and normal and abnormal decision variables. To start with, what is a normal decision variable? Okay, let's just name it like this. Normal decision variable. Efendim?
Hocam, bir arkadaş kamera açısını... tamam, düzeldi şimdi galiba.
Hocam,
kamera açısı...
imkan varsa bilgisayarı sadece tahtının bir tarafına yakınlaştırıp siz de sağ tarafta durursanız biz hem tahtayı okuyabiliyoruz hem de sizin görüntünüz sağda kaldığı için bir ekran görüntüsü var sizin görüntünüzde alan. O kamerada sağ aşağıda bizim okumamızı engelliyor. Eğer sağ tarafta siz durursanız bu sefer sol tarafı okuyabileceğiz biz.
So, when we talk about the normal decision variable, we're actually talking about the decision variable that is greater than or equal to 0. It doesn't matter which decision variable we're talking about here. Okay, it might be a minimization problem, it might be a maximization problem, but a normal decision variable is greater than or equal to 0. This is what we have seen so far. We could have, let's call them abnormal, it's easier to understand like this, abnormal decision variables, in which case the decision variable is less than or equal to 0. Or we could have URS decision variables, in which case the decision variable can be any value between minus infinity and infinity. It can have any sign. It can be negative or positive. We don't know anything about it yet. So these are the abnormal, normal, and URS decision variables. These are the decision variable types for finding the duality. And then with these associated are the normal constraints. Now, when we talk about a normal constraint, we are actually talking about what we expect from a constraint to be in a certain model. For example, in a maximization model, we are trying to maximize our profit, let's say, and we are trying to go to infinity, okay? Go as high as we can in a maximization problem. So, logically, a normal constraint would be trying to limit us, because a constraint's job is to limit us. So it would be trying to get us down, which would mean that for a normal constraint in a maximization problem, let's say in a maximization problem, the right-hand side would be like this, okay? So let's say constraint 1 is less than or equal to b. This is a normal form for a maximization, because in a maximization, we should be limited from top, okay? But in a minimization, constraint, let's go constraint 2, would be greater than or equal to, would have a greater than or equal to sign. Because in minimization, we are trying to go to 0 or minus infinity maybe, depending on the decision variable signs, but still, we are trying to go down as much as we can. So a constraint would be limiting us if it had a sign greater than or equal to. So this is a normal constraint for maximization, a less than or equal to sign, and this is a normal constraint for a minimization problem, a greater than or equal sign. And of course the abnormal constraint, which would be the exact opposite of this one. So the constraint 1 would be greater than or equal to b, and in a minimization problem, the constraint would be less than or equal to b. And there is one more type of constraint, of course, like the URS one, equality constraint. In which case, for both max or min, it doesn't really matter. The constraint is equal to the right-hand side. So, this one is the equality constraint. These are the abnormal ones, and these are the normal ones for us. So, we have to link the decision variables to the constraints. But, let's say these decision variables are for the primal model, and these constraints are for the dual model. Then, a normal decision variable would be linked to a normal constraint. An abnormal decision variable will be linked to an abnormal constraint, and the URS decision variable will be linked to an equality constraint. So, let's just, so you can see that side as well. So, normal decision variables, normal constraints. Abnormal decision variables, abnormal constraints. URS, arithmetically signed decision variables, equality constraints. So how does this work? Let's just have a simple model and take a look. I have to get this. Okay. So this is the most simple version. This version is the most simple version, as you can see. Now, in here, we have the C values for coefficients of the objective function. And now we have the A values for technical coefficients, which give us the constraint coefficients, etc. And then this is the primal for a maximization. And in the dual, we actually have a minimization problem. But this is the most simple one because this is just a normal maximization problem. There are no abnormal constraints. There are no URS constraints. Nothing in here. So this is just the most basic version of taking a dual. But if you want to be, if you want to find something more, let's say complex, we have to dig deeper. Again, the Dakota example, which is a simple duality because it's a normal duality. There are no abnormal, values in there. But let's just create something abnormal then and see what happens there. let's start with an abnormal. This is gonna be a maximization problem. It doesn't really matter which problem it is, but let's just go to maximization. Let's have a minus sign in there. It doesn't really matter. Subject to. The constraints themselves right now aren't important. I can write an infeasible model in here. It doesn't really matter at the moment because we're just trying to find a dual of it. So I will not check if it's feasible, infeasible, or unbounded. I'll just write something. Let's start with 2x1 plus 3x2 plus 2x3 is greater than or equal to 5, and minus x1 minus 2x2 plus 3x3 is less than or equal to 4, and let's have another one, x1 plus, minus 1, 2 plus 2x3 is equal to 3, for example. Now, I have three different constraints, a greater than one, a less than one, and an equality. And I'm gonna try to find three different signs as well. Let's say this is URS, this is greater than 0, and this is less than or equal to 0. Now, we have three constraints and three decision variables, and each of them are different from each other. Okay, this one is a greater than or equal. This one has a greater than or equal to sign, so this is an abnormal constraint for maximization. This one has a less than or equal to sign, so this is actually a normal constraint for a maximization, and this is an equal to constraint anyway. And this one is a URS decision variable. This one is a normal decision variable, and this one is an abnormal decision variable. Now, I want to just take this primal model and transform it. Let's take a primal model and transform it into the dual model. Now, when we are transforming, when we are transforming the model, what we start with is the way, okay, the direction. It's a maximization problem, so it will become a minimization problem. That's for sure. From maximization to minimization. And then I want to, okay, take the transpose of this board, everything in here. So these 5, 4, and 3 values on the right-hand sides of the constraints will become my coefficients. So I know that this will be, the first constraint will be equal to my first decision variable. So the second one will be my second decision variable, and this one will be my third decision variable. And this one will be my first constraint. The second one will be my second constraint. The third one will be my third constraint. So I'll just switch those up, okay? Those 5, 4, and 3s will be coming over here. 5y1 plus 4y2 plus 3y3. Then I'll have to write the constraints. For the constraints, I will just take this part, these values, and transpose them. So it's like this: 2 minus 1, 1. 2 minus 1, 1. So 2y1 minus 1y2 plus 1y3. And then I will have 5, right-hand side of 5. I don't know the direction yet. Is it less than, equal to? No idea. I'm not gonna check those yet. It's the last thing I will do. I will just write the values first, write the coefficients and right-hand side values first, then check the directions. 3 minus 2 minus 1. 3 minus 2 minus 1. So 3y1 minus 2y2 minus 1y3, and this is 3. And last one, 2, 3, 2. 2, 3, 2. 2y1, 3y2, and plus 2y3. Again, I have minus 4 now. And I'm going to have to find values for the directions for, or the normality, abnormalities for y1, y2, and y3. Now let's start with these first. I said already that in the primal model, the constraint is linked to the dual, variables. So the first constraint, this one, is linked to the y1, as you can see here. And the first constraint is abnormal. Okay, because this is a greater than or equal to sign, And this is a maximization problem, so this is abnormal, so y1 should be abnormal as well. Less than or equal to 0. It's a negative z variable. The second one, this one, normal. So y2 is going to be normal as well. The third one, equality, so y3 is going to be URS. Alright, then what about these parts? Now, to check for the first constant, I have to check the first decision variable of the primal model, which is a URS model, URS decision variable. So the constant is going to be inequality. The second one is greater than or equal to 0, which is a normal decision variable. So this would be a normal constraint for minimization. Normal for minimization is greater than or equal to. And the third one is less than or equal to 0. So the third constraint is going to be an abnormal constraint, which is less than or equal to for minimization. So as you can see, this primal model translates into this dual model. And when you solve both of these, this z value is going to be equal to this w value. Okay? The z value will be equal to the w value. The y and x values will be different from each other, of course, but still they are going to be equal. Okay? Whatever the y values or x values take, they are going to be, the z and w values are going to be equal. But of course, there are some, let's say, situations where they're not equal because they don't have any value. How that happens? For example, if one of the models is unbounded, the other one is infeasible. So if one of them is going to infinity, the other one is infeasible, for example. That kind of stuff can happen, so they don't have any values in there anymore, so they aren't necessarily equal anymore. But still, these are special circumstances. If they have a value, if they have an objective function value that's optimal for both of them, then they should be equal. And you can see it from the dual theorem. Now, let's say that we already know that these values are equal. The z star and w star, the optimal values for these models are equal. So, when you're trying to find the z value, the optimal z value, okay, the optimal z value, which is equal to z star, like this. When you're trying to find the optimal z value, you start at a point which is mostly 0 because you don't have any values in there. So you mostly start at a value of 0 and then you try to go up to find the optimal solution. So when you start at 0, you are at the lowest point you can be, most probably. Again, depends on the variables and the coefficients, but still, let's assume that you are at the least value possible at 0. And then you are trying to go up to z star, the optimal solution. Now, when you're trying to go up to z star, you are passing by some values, z1, z2, etc., till you come here. And all these z values are less than or equal to z star. Now, let's assume that you are trying to, solve the dual model. In the dual model, you have w star, which is the optimal solution. Which means that this is the lowest point you can have. So you are trying to get here from a W0, from a starting point. How do you find the starting point? For example, think about the, let's say, two-phase scenario. In the two-phase, you are trying to minimize the A values. After you have minimized the A values, you take the, when you have made sure that the total A values are equal to 0, you take the previous objective function into account and you get a number over there. This is your starting number, okay? So, this is your starting number, which is greater than your optimal solution, and then you start minimizing it. You start going lower and lower. So you get values like W1, W2, etc., till you get to W star. So, we already know that these two are equal. Z star and W star are equal. So, which means that all W values are going to be greater than or equal to all Z values. So, doesn't really matter where you are in the solution. Whatever you find in the W are going to be greater than or equal to the Z value. So what does this mean? How does this help? Well, it helps like this. If you have a primal model that is hard to, crack, hard to, let's say, solve, and you have a dual model that's easier, relatively easier to solve, or at least to start, you can find an upper limit, for example, for your solution. You can say that, okay, I have found one value, any one of these values, doesn't really matter in here. So my solution, my primal solution, the maximization solution cannot be greater than this one anyway. I have an upper limit now, okay? I'm trying to find something maybe, and that something has to be less than this one. I have already found a solution over here. This is helpful, okay? So we can find an upper bound, an upper limit for this one, or going from the other side, we can find a lower limit, because all Z values are less than or equal to the Z star, which is the optimal solution, which is equal to W star. So all Z values are less than all W values, or equal to all W values, which makes them a lower limit, a lower bound for the W. So my solution cannot be less than this value. I can say something like this without solving the solution. So both the primal and the dual can give hints or information about the other one easily. There are other ways of doing that, but still you will see it step by step. We have already seen the non-normal duality part. We have transformed them, but let's just take a look and see what happens in there. We can see that there is 2x1 plus x2, and that x1 plus x2 is equal to 2. We are trying to maximize 2x1 plus x2. And then we have 2x1 minus x2 is greater than 3. x1 minus x2 is less than 1. Now, we have three constraints. The first one is an equality. The second one is a greater than sign, has a greater than sign, which makes it an abnormal constraint for maximization. The third one has a less than or equal to sign, which makes it a normal constraint for maximization. And x1 is greater than 0, which is a normal normal decision variable, and x2 is URS, which makes it a URS decision variable. So the dual in the dual model, the concept is going to be an equality for it. And then when we try to take the dual, we can see it in the bottom side. But take a look over here. We have two decision variables and three constraints instead of the 3 and 3 we have done on the board. We have two decision variables and three constraints. Those two decision variables will be transformed into two constraints. You will have only two constraints because you have two decision variables in the primal model. And with three constraints, you will have three decision variables in the dual model. Okay, this is an important part because you have to make sure that the numbers are always equal. Okay, so when you're converting stuff from primal to dual, so two decision variables become two constraints, three constraints become three decision variables. And as you can see, it's just a normal conversion, and you are getting the same type of conversion that we did here. All the right-hand side values are going up to become the coefficients for the objective function in those duality problems, and all the coefficients over here in the objective function become right-hand side values over there. So 2 and 1 become right-hand side values. 2, 3, and 1 become objective function coefficients. Same thing. And we just check if the decision variables are normal or not, so that we can write the right-hand side signs, okay, the constraint signs. And as you can see, as x1 is a normal decision variable, the constraint that replaces x1, which is the first constraint for the dual model, is going to be a normal constraint, which is a greater than sign for the minimization. So there's a greater than sign over there. And with the URS, it's an equal sign anyway, so we just put the equal sign in. And with the constraints becoming the decision variables, the first one is an equality constraint, which would mean that y1 is URS, it has to be URS. The second constraint is an abnormal constraint, so the y2 decision variable is going to be abnormal, which is less than or equal to sign. And the third constraint is less than or equal, which is a normal constraint for maximization, which makes the third decision variable for the dual model a normal decision variable, which is greater than or equal to sign on the left-hand side. On the right-hand side, it's the same thing with more, let's say more constraints. There's 4 constraints in there, and you can just, find the solution below anyway, and you can just practice on it yourselves. But still, it's not that hard to take the duality. Okay, taking the duality itself isn't that hard, and it might be helpful in more than one way. Now, the expected way is the economic interpretation. We can use dual models to interpret the solutions differently. For example, remember the Dakota problem. In the Dakota problem, we had raw materials, and we were trying to pick which product to manufacture. Okay, we had three manufacturers. Desks, I think, yes, tables and chairs. How many desks or tables or chairs do I want to produce? That was the optimization problem, the maximization problem. I was trying to maximize my profit. But now I can take the dual of this model, and I'm just going to be looking for, okay, which raw materials should be sold, or I can sell at, without a loss, or maybe at a profit for later on, to be head-to-head, okay, with the current profit margin, which means that, okay, someone has come and they're trying to buy my raw materials. Okay, shall I sell my raw materials? If I'm going to sell them, at which price should I sell them, so that I do not lose any profit from my, current production scheme? Which means that I'm producing, let's say I'm just producing chairs. Instead of producing chairs, I'm going to sell the wood, and I'm going to rent out my finishing and carpentry hours as well. I'm going to rent out my workforce. Okay, at which price minimum should those be sold or rented out to make sure I get the same profit instead of, manufacturing chairs? This is the economic interpretation part. If someone comes along and wants to buy my workforce or my raw materials, how should I sell it? At which price should I sell them? This is what we are looking for in the dual model. Okay, in the primal model, okay, I'm trying to profit. I have constraints which are my raw materials or workforce, or etc., and I have prices for those products I'm producing. I'm manufacturing using those raw materials and workforce. But in the dual model, I still have those, but I'm trying to sell my workforce now, or sell my raw materials now, instead of selling my products. So this is just the economic interpretation part. So as you can see, we usually use dual theorem or the duality part to be able to interpret stuff economically. But there are other ways too, of course. For example, I can use the dual theorem, the dual model, to solve the primal model as well. Now, solving the primals, or I can just find the optimal values for the primal just looking at the dual solution. Okay, I don't need to do any other, let's say, iteration to find the primal model if I already have the last table for the optimal table for the dual model. Which means that, okay, I just have to look and see where I can find it, and then I can just find the solution anyway. Now, we already know that there is an identity matrix, so we can know where the, where the solution is easily. But then, let's just take a look. There's a max problem and there's a min problem. We already know how to, find those values in the table, but from that table we can find the, solution for the other problem, the dual problem from the primal problem. Now, as you can see, there are some rules to this one, but you don't have to memorize those rules. You will get used to them anyway by just checking out the table once or twice, because memorizing those or just keep looking at them, just the rules part, is extremely confusing, I would say. But still, let's just take a look from the problem. Now, this is the final table from Dakota. As you can see, we remember the final table. We had 4 constraints if the 4th constraint was included, and it's included here. And we have but the 4th constraint shouldn't be here anyway, because it was later on added. So we can just think of it not belonging there, and we can just remove the 4th constraint, but it doesn't really matter. And we have the dual for the original question without the 4th constraint, because there is no 4th, y value in there. There is no y4 in there, so we don't have the 4th constraint in the primal model for that one. But still, it's okay. We can have them or not. It doesn't really matter right now. But still, here we have y1, y2, and y3 for the dual model. Okay. To find the solution, to find the values of y1, y2, and y3, we have to check the slack values in the coefficient function. Let's say in the final table, over here, let's just use the mouse. Over here you can see that 0, 10, and 10. These three values are your y values for your optimal solution. So how can I be sure? Just use them and put them into y values. 0, y1, okay, y1 is 0, so there is 48 times 0. y2 is 10, so 20 times 10, 200. And y3 is 10, so 10 times 8, 80, 280. So the minimization problem solution is 280, which is the same solution for the maximization, which was 280. So they're equal, no problems there. And you can just use those to find the values downstairs as well, in the constraints as well, 0, 10, 10. You can just use them to find all your slack values, which you will find out that they are actually equal to those values, 0, 5, 0, the x value. Because as I said earlier, the decision variables in the primal model is linked to the constraints in the dual model. And the constraints in the primal model is linked to the decision variables in the dual model. So as you can see, in the optimal solution, those values 0, 5, 0 are actually your slack or excess values for your dual solution. And those values 0, 10, 10, which comes from your constraint slacks, are actually equal to your optimal solution values for your y values, your decision variables in the dual model. So we can just read everything over here easily. Let's just try 0, 10, 10. We have all the found that this is 20 and 80. Let's check here 0, 10, 10. This is 60, 60 is equal to 60, so the excess value is 0. 0, 10, 10. This is 20, this is 15, so 35 is greater than 30. It should be 5 here, minus 5 here. So the E value is, the excess value is 5. And over here, again, 0, 10, 10. We have 20, 20 is equal to 20, so the E value is 0. Yes, 0, 5, 0, the same thing. So I can just use the final table from the primal to find the solution for the dual as well. It's pretty simple actually. The first line is giving us everything we need actually. But there are still some instances where we don't have any values for the optimal tables. So this is where complementary slackness comes in. Now, the complementary slackness theorem, tümler gevşeklik in Turkish, this theorem says that if we know which decision variables are in the solution, which decision variables are in the optimal solution, let's say, then we can find out the values for everything using that one. Now, there's a simple rule here, as you can see in the presentation as well. Like that. Now, the rule says that if one of the constraints, or if one of the, let's start with decision variables, if one of the decision variables is in the solution, if it's an basic variable, so which means that it's an active variable as well. So if it's a basic variable or if it's in the solution, then for the dual, let's say for the primal, let's say basic variable, which means it is in the solution. So for the dual, first of the constraint related to it is going to be in the solution as well. So the constraint will be active. Okay? Because they are related, remember. The variable, if the variable is a basic variable, then the constraint should be active. Okay? The basic variable in the primal gives an active constraint because they are related. So if one of them is in the solution, the other one should be in the solution as well. So what happens here? If this is a basic variable, this is greater than or equal to 0. This might be, this might be a 0 value or a greater than value. It doesn't really matter. But if the constraint is active, the S or E value should be equal to 0. Because if I'm an active constraint, then the solution is on me, then my distance to that solution is always 0. So, if it's a basic variable, it's going to be greater than or equal to 0. If it's a constant active constraint, then the S or E value is going to be 0. So if you can check it over here, let's say this is x1 and this is E1. So x1 times E1 is going to be 0 always. It doesn't really matter which value x1 takes, E is going to be 0 always. If this is a non-basic variable, then it is not in the solution. which means that the constraint is non-binding or not active or passive, I don't know, we can write anything, which means that the S or E value is greater than or equal to 0. It might still be 0, which would make it a degenerate constraint, greater than 0, but over here, the X value is equal to 0 because it's a non-basic variable. So once again, X2 times E2, let's say, is going to be equal to 0. Of course, we can read it backwards too. So if the constraint is active, then the variable is basic. So again, the same solution. So what we know over here is, for any variable, okay, the constraint, the dual constraint that is, related to it, has a multiplication of 0, the excess or slack value of the dual constraint. Same thing over here. It doesn't really matter if it's a basic or non-basic variable. And the same thing goes for y1 times s1, y2 times s2, etc. They are always going to be equal to 0 anyways. So what does this give us? Now this gives us a way to solve a dual or primal model without using any, let's say, iteration. Okay? We can just find out what we are looking for without making any iterations, as long as we have an optimal solution. Okay? So let's just start with the Dakota. Now, we already know the model, as you can see on the left-hand side, and we already know the dual model on the right-hand side. We know both of these. And it says that, okay, the optimal solution is now. We know the optimal solution. Let's start with the optimal solution then. We have already found the optimal solution to Dakota beforehand, and we already know the values for it. Doesn't really matter at the moment, but still. What we just need is to find which, let's just clear this one, yes. Now what we need is to find out which, let's just write them. X1 is equal to 2, X2 is equal to 0, and X3 is equal to 8. S1 is equal to 24. S2 is equal to S3 is equal to 0. Now, from here, we have some stuff we know. X1 and X3, these two are basic variables because they're inside the solution. And S1 is non-binding. S1, S2, and S3 are binding. So it's a non-basic variable as well. Now, this one, okay, I already know the E1, E2, and E3, and I already know for over here Y1, Y2, Y3. Now, these are the primal model versions, and these are the dual model versions. Now, I know that the basic variable, X1 is a basic variable, so in a dual problem, the first constraint should be binding as well. It should be, an active constraint, which means that this is going to be 0. And I don't know that this multiplication should be 0 anyway, so I can write this as 0. No problem with that. Over here, it's a 0, so this can be anything. It can be greater than or equal to 0. There's an 8 over here, so this should be 0. There's a 24 over here, so this should be 0. There's a 0 over here, so this can be greater than or equal. It doesn't really matter. Now, from these parts of information, from these parts, we can just construct the model very easily. For example, ignore the objective function for the dual problem. Just focus on the constraints now. For example, I don't know that y1 is equal to 0, right? So I can just remove y1 from the solution completely. So that I have 4y2 for the first constraint plus 2y3. Okay? And I don't care about right-hand side yet. I'll just write the solutions, the constraints without y1. I have 2y2 plus 1.5y3. I have 1.5y2 plus 0.5y3. Now, from here, I also know that E1 is equal to 0 and E3 is equal to 0. So, there is no E1 or E3 here. These are just equal to 60 and 20. And I also know that there is an E2 here, plus E2 or minus E2, of course. But still, there's an E2 over here, which is going to give me 30. Now, if I look at these three, let's say, equalities, there is this one and this one. Two unknowns, two equalities. I can just solve this. It's easy. Multiply this by 4, so that I have the same y3 coefficients, and just subtract one from the other. If I multiply this by 4, I will get 6y2 plus 2y3 is equal to 80, right? So if I just subtract from this one, I will just get 2y2 is equal to 20, which means that y2 is equal to 10. If y2 is equal to 10, then y3 is going to be equal to 10 as well, right? Which is equal to y3. So put 10 over here, I will need another 10 to get to 80, so y2 is equal to 10 as well. What about y1? Well, y1 is already 0. I already know what y1 is. Okay, I'm missing just e2. So I'm just going to have to find e2. Okay, this is easy as well. Put these values over here. 20, 35, so it should be 5. All right, I'm done. I don't need the optimal table. I don't need the, I don't need to make any iterations. I just need to see the first table, let's say the standard form maybe. Even that's not important. I just need to see the primal model, and the dual model, of course, can be derived from it. And I just need to see which, let's say, I don't even need to know their values, okay? I just need to see which variables are basic variables, which are in the solution, which includes S values as well, of course. So if it just said to me that x1 is inside the solution, x2 is inside the solution, and s2 and s3 are 0, and s1 is inside the solution, and x2 is 0, that will be enough for me. So it's all it needed to say was basic variables are x1, x3, and s1. That would have been enough to find the values for both sides. Okay. If it just said this is how you solve it, this is what you have got at the end of the solution, it will be enough to find everything over here and everything over here as well. All right? Because if it says that these are basic variables, for example, x1, x3, and s1 are basic variables, which from here I can say that s2 and s3 is 0, x2 is 0. If I know these two facts, x2 is equal to 0 and s3 is equal to 0, then I can just find everything else the way I did over here. It doesn't really matter. I don't need to have those values, okay? We don't have those values over here. We just have the signs. Are they equal to 0 or can they be greater than or equal to 0? And using those, we will just find the values over here. Okay, any problems, any questions up until now? Okay, then let's take a break.